Welcome to example number 7. It's an interesting question about an airplane and with a propeller that's turning around at 1500 revolutions per second, but we're asked to figure out what would be the maximum radius that this propeller would have to be so that when the air is deflected off of the tip of this propeller, it will not go any faster than 300 meters per second. There's a kind of a tough problem to visualize here. So let's just take a look at just the propeller turning around here. Let me redraw that over here. So you can imagine this propeller as it's turning around and around in this counterclockwise direction. If you look at the air at the very tip of, say, this section of the propeller, it's being deflected offwards at a tangential speed. I'm going to label that as V tangent. So this is sort of a front view of the propeller. And then it's moving off at a constant angular velocity of 1500 revolutions per minute, which we'll probably have to convert to radians per second in our problem, but we'll do that in a minute. However, how do we visualize this plane speed? So we'll need to kind of look at it from, say, a side view of the airplane. So here's the nose of the airplane, and there's the propeller, and we see that the plane is moving forward at a velocity of 90 meters per second. I'm going to label that as V of the plane, which is equal to 90 meters per second. So then, where does this 300 meters per second work into it? Well, you see, the air is being deflected both tangentially, and then also because the airplane is going forward, it's going to be pushed backwards. And so there's two velocity components, both perpendicular to each other, causing it to go in one net direction. Let's take this velocity here and just simply draw it over here. And that's V tangent. And really, the resultant velocity is right along here. So I'll draw that here, right along the diagonal of that rectangle. And this is the velocity of the tip, which can't be any larger than 300 meters per second. So we really know this component and the one that's along the hypotenuse, the resultant velocity, but we do not know the tangential velocity. But we could figure that out. So we know this side, V of the plane, which is 90. We do not know V tangential, but we do know the hypotenuse of this right triangle. That is V of the tip, which is 300. So hopefully you can see that we can use Pythagorean theorem here. So V of the plane squared plus V of the tangential velocity squared equals V of the tip squared. Plane we know is 90 squared. Tangential we don't know, but we can figure that out now. And the tip was 300. That will give us the velocity tangentially to be 286.18 meters per second. I'll just round that up to 286 meters per second. So there must be some relationship between the tangential velocity and the angular velocity. Remember that the tangential velocity is really the linear version of the angular velocity. So V tangential is equal to omega times r. So if we want to find the radius, then we just need to divide the tangential velocity by the angular velocity. And that's all good, but except we need to convert that to radians per second. So let's do that. Omega is 1500 revolutions per minute. We need to convert revolutions to radians. So we have 2 pi rads on the top and 1 revolution on the bottom. And then we need to get rid of minutes, so we'll put minutes on the top and then 60 seconds on the bottom. So this will give you an angular velocity of 157 rads per second. So now we're ready to figure out that radius. So we're going to be taking the tangential velocity of 286 meters per second and dividing it by the angular velocity of 157 rads per second. And that will give you an answer of 1.82 meters. If the radius was anything larger than 1.82 meters per second, we would end up getting air that would be leaving the airplane tangent or not tangentially along the tip here at a velocity that is greater than 300 meters per second, which would be faster than the speed of sound.